Hi everybody. So this lesson 4.5 is part 1 of 2. We have 2 lessons remaining in this unit. And this one's going to talk about Laplace transforms. Okay, so Laplace transforms, if you just glance in the textbook, seems like a rather intimidating topic. But what they actually mean is relatively straightforward. Laplace transforms literally transform a function into an algebraic one. Okay, so transferring something like e to some exponent t, whatever the coefficient a is behind it, into something that's algebraic. So we're going to show how the Laplace transform, for example, of this function is actually equal to simply this. Okay, now we can use Laplace transforms to do several things. We're going to show you how to solve differential equations with them. And more specifically, if you remember when we talked about finding particular solutions, a Laplace transform will allow us to find the particular solution directly. Okay, remember we had that y was equal to our general plus our particular solution. The Laplace transform is going to allow us to find this without having to guess or make estimates as to what our final function is. And we also don't have to have a lot of specifics when it comes to the form of the equation like we had to have previously. Okay? So to start off with this, I'm going to show you what the literal definition of a Laplace transform is. And then we're going to do an example following this definition to see how a Laplace transform, such as this one here that I've drawn or written on the right here, is actually formed. So a Laplace transform, we have 2 different notations of it. Okay, so we start with a function t, so f at t, and the Laplace transform is capital F at s. Okay, so s is replacing t. Alternatively, you can write it with the L. I wrote an L here. A lot of times you'll see it with the cursive way to write a capital L, like that. Okay, or let's draw it a slightly better way, like that. And it's equal to the Laplace transform of that function f. Okay, so both these notations mean the exact same thing. And what they're equal to is actually the integral from 0 to infinity of e to the exponent negative s times t. And remember, s is going to end up replacing t, so it's kind of important that's there. And it's multiplied by the function that we started with, which is f at t. Okay, so this equation is what we're going to use to find a Laplace transform. Okay, and using that Laplace transform, we're going to be able to solve differential equations when we talk about that in the next lesson, 4.6. Okay, so why don't we start by simply doing an example using exactly this formula that we have here and solving for a Laplace transform. So let's start with a function. Remember, I said that we started with a function of t. In this case, we'll use the sine function, sine of a times t, where a is a constant. And in this case, it's a function of t. Okay, so t is our actual function here. If we use our definition of a Laplace transform, we have the integral from 0 to infinity. Remember, e to the exponent negative st. You can think of this as similar to the integrating factor that we had when we did differential equations. Similar to, not the same, okay? Times our function that we started with, f at t. So if we substitute that in, we get the integral from 0 to infinity of e to the exponent negative st times sine of at dt. So what we have here is an integration formula, okay, with 2 functions multiplied together. Now, we could use integration by parts, okay, but it's difficult. because we have a function e, and if you remember, the derivative of the e function is just e times the derivative of the exponent. And with sine, the derivative is cosine. So we never really get rid of one or either of those functions. So instead, if you remember back to our second unit, we talked about integration using tables. Well, there happens to be an integration formula using tables, using those tables that satisfies this. E to the exponent a times u times sine b times u du. And this is the integral that comes out of it. Okay? So we're going to use that, substitute in our appropriate variables, and then see how we can solve the integral, because remember, it's from 0 to infinity. In this instance, it's just talking about the solution to the integral. So for our function, okay, we have e to the integral of negative s times t times sine of at dt. Okay, remember, this is a function of t, so we assume that s here and a are constants. Okay, it's unfortunate that we have an a here and an a in the integration by tables, but it is what it is. So if we substitute in, remember we have a here and we have a negative s here. So a is equal to negative s. For the a piece here, it's actually equal to b in this. That's why it's confusing. Okay, but all I'm doing is comparing one to the other. So b in our integration by table is actually equal to a in our initial function. And for u here, it's actually just equal to t, because remember, ours is a function of t. This is a generic form in the table, which is a function of u. So if I substitute those in, I get e to the exponent negative st times negative s sine of at minus a of cos at divided by negative s squared plus a squared. Negative s all squared actually comes out to s squared. Okay, positive s. So here we have a function at infinity and a function at 0. So remember, we would substitute in infinity here and then subtract by the same function, substituting in, it's a bad arrow, substituting in 0. But if you remember, substituting in infinity, it's a little bit tricky. And oftentimes we had to use either limits, or we had to use limits, and if we ended up with odd solutions, because remember this is a fraction, we would get 0 over 0 or infinity over infinity. And in that case, we had to use L'Hopital's rule. But before we used L'Hopital's rule, we tried to evaluate the limit. So we're actually going to just rewrite this as the limit as t approaches infinity of that function, because we're going to substitute in infinity at the end, minus that same function where we substitute in the lower bound, which is 0. So I've substituted it into all three locations here. And there's a couple items to note here. Sine and cosine, they're basic functions, okay, always go between positive and negative 1. Okay, so what you might not know is as sine and cosine approach infinity, their value just approaches 0. Okay, so what happens is that this is 0 minus 0, okay, which just becomes 0. E to the negative st can actually be written as 1 divided by e to the st, which is actually 1 divided by e to the infinity if you substitute it in, which 1 divided by any number that's that large is simply 0. So you're left with 0 times 0. And in the denominator, we have just some number here, s squared plus a squared. We're not substituting in infinity anywhere. So if we have 0 divided by any number, that first term means that that is just 0. Okay? So as we take that limit and substitute in infinity, that's what we get there. For the second term, we have, again, taking it in steps, e to the exponent negative s times 0. Well, e to the exponent 0 is simply 1, so that becomes a 1. Sine of 0, remember I drew the sine function over here. So sine of 0 is simply 0. But cosine of 0, remember cosine is out of phase with sine, is actually 1. And the denominator stays the same, except this becomes positive s squared plus a squared. So substituting this in, we have 1 times 0 minus, we have a times 1, which is just a, divided by s squared plus a squared. So if we do 0 minus that, our Laplace transform ends up as a divided by s squared plus a squared. Okay? So this was a very long, process to think through this. This actually touches on a lot of the topics that we've covered in this course. Okay, so everything kind of comes together to look at doing this integral for Laplace transform. But thankfully, I will not make you have to do this calculation to determine a Laplace transform. Laplace transforms are very similar to when we did integration using tables. They are documented for specific functions. So all of the Laplace transforms we're going to need for this course will be provided to you in a table. And we're going to use those Laplace transforms to look at some properties of them. And then in the next lesson, we're going to solve for differential equations using those Laplace transforms. So I showed you this solely so you can see and understand how these come about, why there's an S term, why there's an A, and in some instances a B or a second constant. But outside of that, I just want you to use them, okay? So here is the big table of Laplace transforms. This is a very small snapshot of all the Laplace transforms that we know. There's more in other textbooks. There's more and more advanced textbooks. Different textbooks provide different transforms depending on what they want to use in their course. These are the ones that we have provided with our textbook. Okay. Again, this is on your Unit 4 formula sheet. They're not things I would ever expect you to memorize. One thing I want to note is we just did sine of AT. And you'll see the Laplace transform is a divided by s squared plus a squared. Okay, so what we just determined in our previous slide is one of the transforms here. So the first column we have is the actual function f at t. And what that's actually equal to is the inverse Laplace transform. So in some cases, we're going to start with a function that looks like this. And you can actually find the inverse Laplace transform, or the function that it came from, using this table as well. Okay. The second column shows the Laplace transform of a given function here. Again, all of these are shown as f at t. Could be f at x, could be f at anything really, right? The basic form you see is always f at t for the function. So t usually, or in a lot of instances, standing for time. And the Laplace transform having s, okay? Or capital F at s. Or alternatively, remember the cursive L of the function. Okay, so this table will be the reference piece that we use. And in my examples, I will tell you, you can see I have them numbered here from 1 to 20. I will tell you which number I'm referring to. So when you're watching this lesson, what I recommend for you is to take the formula sheet and actually have the Laplace transforms with you from this point forward. Okay, because you're going to see me name which of these Laplace transforms I used. So it's helpful for you to kind of see the form of it to get familiar with solving them. All right, so using that table that I just provided, again, I recommend that you have the formula sheet in front of you for all of our examples moving forward. Find the Laplace transform of the function f at t equals 3t minus sine of 3t. So looking at our table, you're looking for two aspects, a function of t and a sine function with the same value, 3t, okay? Because you're looking for the same constant. You'll notice that they're They're structured that way a lot on this formula sheet. And if you scroll down, you get to number 8. So number 8 in our list is AT minus sine of AT. Okay. Well, in this case, that must mean both are functions of t. Check that off. And both of them have the same coefficient behind them, a, which is 3. Meaning that a is equal to 3. So using the Laplace transform, okay, for number 8, that's equal to a cubed divided by s squared times s squared plus a squared. Well, a is 3, we substitute it in, and we get 3 cubed divided by s squared times s squared plus 3 squared. Which means we get 27 in the numerator, 3 cubed, divided by s squared times s squared plus 9. Okay? So you can see that you're just looking for those same kind of correlations that we did when we did integration by tables. Okay, looking for those constants and looking for what they're a function of t, a sine function, a function of e, a cosine function, etc. Okay. Our second example, find the Laplace transform of the function f at t is equal to e to the exponent t. Well, if we look, we're looking for just a function e to the exponent t. And that's satisfied by number 3, which is e to the negative a times t is equal to 1 over s plus a. Okay. Well, in this case, we have that the value behind t is 1. And we have a negative here. So that means that the negative a that's there must be equal to whatever the coefficient is behind this, which is 1, in order for us to use this. Meaning that, dividing both sides by negative 1, we get that a must actually be negative 1. So what that means is the Laplace transform of e to the t, you could also write it as, remember, f of s. And you can also write it as the Laplace transform of just f. Okay, whatever way you prefer, they're all the same. You might see me use them interchangeably. I do like to write the fancy cursive L. Okay, so I'm just going to give you a heads up on that. So that's equal to 1 divided by s plus a. In this case, it's a negative number, so it becomes s minus 1, right? Because what we would have had is s plus negative 1 for a, which means it's simply 1 over s minus 1. So this is a great example of showing you how it changes what is a function such as e, the Laplace transform, changes it into an algebraic expression. Okay? 1 over s minus 1 is far different when we're looking at differential equations specifically than the function e. Okay? And we're going to see some applications of Laplace transforms, again, in our next lesson, 4.6. This lesson's focusing on what they are, how to find the Laplace transform, and some properties to solve for them. Okay, so let's look at one more example. Find the Laplace transform of the function f at x equals x sine of 2x. So I used x here, but again, it doesn't matter, right? Normally it's written as f of t. It's written as f at x here, doesn't change it. So we're looking for, if you wanted to rewrite this in terms of t to make it easier to use the tables, you can. We're looking at f at t would be equal to t sine of 2t. So we have a sine function multiplied by by a function of t, and we have a value before it of 2, which will be one of our coefficients, or constants, either an a or a b, depending on what it says in the table. So looking at this, we actually can look at number 16, which is t sine of a times t, And the Laplace transform is actually equal to 2 times a times s divided by s squared plus a squared all squared. So knowing this, if we want to fit this into the form, then our value a here must be equal to 2, right, which is the coefficient in our question. So the Laplace transform of this function, again, you can just write it as f if you'd like, is equal to 2 times a, which is 2, times s, divided by s squared plus a squared, which is 2 squared, all squared. Simplifying this, 2 times 2 is 4, so we have 4s divided by s squared plus 4 all squared. Okay, so you can see we're writing this as terms of monomials and binomials. Okay, all kind of polynomial functions, as opposed to writing them as a sine function or a function of e. Okay, so like I said, these literally transform the function into another form that we can use. Okay, so I mentioned this earlier when we talked about Laplace transforms. You can actually start with a function that's in the form of a Laplace transform. Okay, so something like this. Capital F of s is equal to s divided by s squared plus a squared. And using this as an example, okay, we have that s divided by s squared plus a squared actually fits to the Laplace transform of cosine of a times t. Okay, so the inverse Laplace transform starts with a function, okay, and I'll always give you them typically with the s here, with the exception of when we might talk about an application. But in most instances where I'm purely looking at the math behind them, I'll normally give them to you something like this with an s in it. Okay, that means is working backwards that this function s divided by s squared plus a squared, if you did the inverse Laplace transform to revert it back to its original form, it actually is the sine of a times t. Sorry, the cosine of a times t. Okay, I said sine, but you know what I mean. So this looks like a simple example. I drew it. I took it directly from the table. It can get much more complicated than this. Some of our examples we're going to look at the same method we used when we did integration by partial fractions. Okay, so let's look at a few more examples. So find the inverse Laplace transform of the function capital F of s is equal to 2 divided by s plus 4 squared plus 4. So again, we're stopping to look at this function and we realize a couple things here. We see the only value of s is here in this first bracket. We see that our denominator has two functions. We have the first set of brackets all squared and then a constant value. And in the numerator, we just have a constant. So looking at what I have available to me, the only ones that have separated pieces, which is in the denominator here, of a function like this squared plus a constant, are either numbers 19 or 20. Okay? The difference being number 20, I'll write them both out so you can see the difference. So 19 is e to the negative at sine b times t. And the Laplace transform is equal to b divided by s plus a squared plus b squared. And 20 is similar, e to the negative at cosine of bt instead of sine. And that's equal to s plus a divided by s plus a squared plus b squared. So the difference here, number 19 has just a constant. 20 also has a function of s in the numerator. So we know that based on our initial function, there's no s here. It's just the number 2. So we can forget number 20, but otherwise, it looks like number 19 falls within it. What we see here is that b would be equal to 2, and b squared is equal to 2 squared, which is equal to 4. which matches those, meaning that A must be the value within the brackets here. So A must be equal to 4. Okay? Again, just finding that data within what you're provided. So it fits this transform, meaning that the inverse Laplace transform, that big function of S, is equal to e to the negative a, which is 4, so 4t, times the sine of b, which is 2 times t. Okay? So this is kind of the most basic form to find the inverse Laplace transform. You're purely looking at that value and looking at what it matches to on the tables. But it can get more complicated than this, okay? Because there's some properties of Laplace transforms we need to look at so that we can look at more complicated ones using partial fractions. The property that we're going to look at is called the linearity property. And what it says is that the Laplace transform of two functions added together, okay? So f plus g, and the a and b here are just constants, right? So it doesn't matter if it's 2 times that function, 12 times that function, whatever it is. A and b are just constants, okay? So a and b are constants. F and g are functions typically of t. So f of g and g of t, or f of t and g of t, sorry. If they're added together, just like in derivatives and integrals, you can find the Laplace transform of them separately. So it's equal to a, or that constant, times the Laplace transform of the first function, plus b times the Laplace transform of the second function. Remember, this is very similar to if you have two functions, derivative of x plus y with respect to, let's say, x. That's the same as the derivative of the first function plus the derivative of the second function. Similarly, remember, if we had the integral of, let's say, x plus 2x dx, that's the same as the integral of x plus 2, because it's a constant, times the integral of x again. Okay, so you can separate them out, and the same thing is true for Laplace transforms. Okay, that's a very, very useful property. You're going to see why it's so useful in the next function. And what it tells you is it doesn't matter if you have two separate functions. You can still find the Laplace transform by just looking at them as individual functions and finding their corresponding Laplace transforms that way. So you don't have to look for specific, combinations or in a lot of these instances, try and redefine or move around the function to fit into one of these 20 formats that I've provided to you. There's other ways to try and solve them. So in this example, we're going to look specifically at this linearity property. Before we do 2 more examples to finish this lesson that look specifically at combining, finding the inverse Laplace transform with this linearity property. So the first question, find the Laplace transform of the function sine 3t plus 2 cosine of 3t. Okay? Well, looking at this, we have 2 functions combined together, or added together, I should say, but both of which are specifically on our Laplace transform table. So we have number 5, which is cosine of a times t. I always get those two mixed up. Number 5 is cosine of a times t, and that's equal to s divided by s squared plus a squared. And number 6 is sine of a times t is equal to a divided by s squared plus a squared. Now you'll also notice that we have a 2 behind the cosine, but remember, for the linearity property, the Laplace transform of a function f times a constant a plus a function g times a constant b is the same as a times the Laplace transform of the first function plus b times the Laplace transform of the second function. So in this case, f at t is sine of 3t, g of t is cosine of 3t, and for the purposes of our Laplace transform, the constant behind the sine function is 1, and behind the cosine function is 2. So first, let's find the Laplace transforms, and then we'll put them in this equation to find the overall Laplace transform. Okay? So for the first function, sine of 3t, well, we know that a must be 3. So the Laplace transform of sine of 3t must be equal to a, which is 3, divided by s squared plus a squared, which is 3 squared, which gives us 3 divided by s squared plus 9. The Laplace transform for the second function, cosine of 3t, is equal to s divided by s squared plus a squared, which is 3 squared, or s divided by s squared plus 9. So now, using this linearity property, we have the Laplace transform of sine of 3t plus 2 times cosine of 3t is equal to, and I'll put it on the next line just so you can see it, 1, because remember there's nothing behind the sine function, times the Laplace transform of the sine function, 3 divided by s squared plus 9, plus 2 times the Laplace transform of the cosine function, which is s divided by s squared plus 9. Multiplying this out, we get 3 over s squared plus 9, plus 2 times s over s squared plus 9. Now you could leave it like that with two separate transforms, or you'll see that they have the same denominator in this case, s squared plus 9. So you can simply add them together, and you get 3 plus 2s divided by s squared plus 9. Okay, so that is the benefit of using the linearity property. Okay, combining everything that we've learned in this lesson, you're going to see us, when I say us, I mean me, do the next two examples where we're trying to find the inverse Laplace transform. Okay, and we're going to need to use the linearity property as well as what we know about Laplace transforms in terms of the table. And as I've mentioned previously, we're going to have to look at using partial fractions here in order to find our final solution. So find the inverse Laplace transform of the function f of s, or capital F of s, is equal to 1 over s squared plus 2s minus 3. So in this example, we have f of s is equal to 1 divided by s squared plus 2s minus 3. And you can actually factor the denominator because positive 3 and negative 1 multiply to negative 3, and they add to positive 2. So you can factor this as 1 divided by s plus 3 and s minus 1. Now remember, the linearity property means that two functions have to be added or subtracted to one another in order to be able to take the Laplace transform of them individually. In this case, we have two functions of s multiplied together in the denominator. But remember, we can separate them by saying it's equal to a divided by the first term, s plus 3, plus b divided by the second term, which is s minus 1. Okay? So remember, in partial fractions, we have to now solve for a and b. And we start by multiplying both sides by both factors. Okay? So they cancel on the left-hand side, and we're left with 1 is equal to a times the s plus 3's cancel, but the s minus 1 does not. Plus b times the s minus 1 cancel here, but the s plus 3 does not. So now if you remember, we multiply this out. We get 1 is equal to a times s minus a plus b times s plus 3b. Now remember, to solve these, we group them together on each side. So with the functions of s, we have a plus b, and that has to be equal to all the functions of s on the left-hand side, and there are none. So that must be equal to 0, or a is equal to negative b if we solve it that way. Next, we have that negative a plus 3b has to be equal to whatever we have for constants on the left-hand side, which is simply 1. Okay? So, taking what we know, we can substitute in negative b for a, and we get negative b plus 3b is equal to 1. So a negative and a negative make a positive. So we have b plus 3b, which is 4b, equals 1. So b must be equal to 1/4. Meaning that since a is equal to negative b, a must be equal to negative 1/4, because it's just the negative of the b function. So now substituting those in, we have that f of s must be equal to a, and I'll write it as a fraction beside it, negative 1/4 times 1/s plus 3. I just wrote the a to the left here. I thought it was easier rather than having to write the fraction in and separate it. It also makes the function that we can take as the Laplace transform easier, because it's 1 divided by whatever the function is, in this case s plus 3. Plus b, which is also 1/4, times 1/s minus 1. Okay? So now, remember, I'll do it in green. The Laplace transform of a times the first function plus b times the second function is equal to a times the Laplace transform of the first function plus b times the Laplace transform of the second function. Okay? So you can write this as two separate Laplace transforms. Okay? Looking at our table, in both cases we have a 1 in the numerator, and we have s plus or minus something in the denominator. And that corresponds, looking at our table, to number 3, where we have e to the negative a times t is equal to 1/s plus a. Okay? So we know what the Laplace transform is. Okay? And both these are in the form on the right, meaning that to find the initial function, we got to find the reverse Laplace transform. Okay? And if we do that, we know for the first function, s plus 3, that a must be equal to 3, so for function 1. For function 2, a must be equal to negative 1, right? Because we have s minus 1. So knowing that it fits into those forms, we can find the inverse Laplace transform of the entire function by taking our constants, negative 1/4, times the inverse Laplace transform of 1/s plus 3, plus 1/4 times the inverse Laplace transform of 1/s minus 1. So this linearity property works both for finding the Laplace transform and for finding the inverse Laplace transform, just like when we talk about derivatives and integrals. Okay, it works going both ways. So knowing that it fits into this number 3, okay, we know that the Laplace transform, the inverse Laplace transform of f and s is equal to negative 1/4. For the first one, we have e to the exponent negative 3t plus 1 over 4 times e, and in this case, a is negative 1. So we get negative times negative 1 times t. So two negatives make a positive, and that means we have negative 1 over 4 e to the negative 3t plus 1 over 4 e to the positive t. Okay, so by using partial fractions, we broke it up into two separate functions that we knew the Laplace transforms of using this table. And what's important for you to know is this linearity property that I have sitting up here, well, that is not the color I wanted to use, is very important. Okay, and you can see that it works both ways, finding the Laplace transform and then working backwards and finding the inverse Laplace transform. Okay. So in that first example, I gave you an easy one, right? One in the denominator you can factor. But remember, we had other cases. We had cases where we have repeated factors in the denominator. In this case, find the inverse Laplace transform of the function capital F of s is equal to s minus 1 divided by s squared times s minus 4. So we have an s squared term here, which means that we have a repeated factor of s. Okay? So it's a little more math in this example, but otherwise, you know, it's going to be the same. We're going to get to functions at the end that we can then find the Laplace transform of. So we start by writing s minus 1 divided by, actually I'm going to move it over so we can do our multiplication. S minus 1 times s divided by s squared times s minus 4. And that's got to be equal to, remember, for repeated factors, we have to carry it twice. But we do a divided by s plus b divided by s squared. Remember, you show both factors, but one of them is squared and one of them is just the factor, you know, originally or to the exponent 1. Then we have plus c times our third factor, s minus 4. Now we follow the same method here for repeated, or for, even if it's repeated factors. We multiply both sides by everything in the denominator. So s squared times s minus 4. Okay? If we do that, they cancel on the left-hand side. And we're left with s minus 1. On the right-hand side, for the first term, just one of the s's will cancel, meaning we have a times s minus 4. For the b term, the s squared term entirely will cancel, so we're left with b times s minus 4. And for the last term, just the s minus 4 cancels, so we're left with c times s squared. So multiplying this out, we get s minus 1 is equal to a times s squared minus 4a plus b times s minus 4b plus c times s squared. Starting with the highest level exponent, on the left-hand side, we do not have any squared terms, so we'll have 0. On the right-hand side, we have a times s squared plus c times s squared. So in other words, a is equal to negative c. And you know, when we get this many terms, I do like to cross them out to know that I've used them. For the s term, we have on the left-hand side just a 1 behind the s. On the right-hand side, we have just the function b. So we know that b is equal to 1. Okay? Actually, that's not quite correct. The reason for that is I multiplied in the as term wrong. So we have as times negative 4, which is negative 4a times s. I knew something was wrong when I was comparing my solution. So what that means is, for the s term, on the left-hand side we have 1, but on the right-hand side we actually have two terms. Negative 4a times s plus b. And that's crossing out these two terms here. For our final one, on the left-hand side for constants, we have negative 1. On the right-hand side, we have negative 4 times b. So solving for b by dividing both sides by -4, we get that b is equal to 1 divided by 4. Okay? And I'll circle that in a different color so we don't forget about it. Now using the second equation, we have 1 is equal to -4a plus b, or 1 is equal to -4a plus 1/4. Bringing the 1/4 to the other side, we have 1 minus 1/4 is equal to -4a. So 1 minus 1/4 is 3/4. So 3/4 is -4 times a. Dividing both sides by -4, we get -3/16 is equal to a. So again, I will put a different color around that. So lastly, we know that a is equal to -c. So -3/16 is equal to -c. Dividing both sides by -1, we get that c is positive 3 divided by 16. Okay? So now, writing out our partial fractions, we are left with, and I'll put a line here just so you can see the difference, -3/16 times a, which is 1/s, plus 1/4 times 1/s squared, using the b term, plus 3/16 times 1/s minus 4. Now we have two types of Laplace transforms here. Remember, we get to use the linearity property, so we're looking at each of these terms individually. Actually, we have three different types here. So for the 1/s term, it's the very first one in the Laplace transform, number 1. So we have that 1, the Laplace transform for is 1/s. For the second term, 1/s squared, we actually use number 2. So Laplace transform number 2 says that some function t to the exponent n minus 1 over n minus 1 factorial is equal to 1/s to the exponent n. Whatever the exponent is, okay, it could be 1, 2, 3. So this is used mostly for higher level exponents. In this case, we are using the squared term. For the third term, we have s minus 4, which uses number 3. Where we have e to the negative a times t, the Laplace transform is 1/s plus a. Okay? So for equation 1 here and 2, it's relatively straightforward. For equation 3, we have to know what a is. So a must be what's in the bottom here, or a is equal to -4, right? Because it's that second value in the denominator. So now, if we find the Laplace transform, or sorry, the inverse Laplace transform of each, for the first one, we have -3/16, and that's simply times 1, right? Because the Laplace transform of 1/s is 1, plus 1/4 times, in this case, it's t to the exponent 2 minus 1, because the exponent here is squared, divided by 2 minus 1 factorial. And our last one is plus 3/16 times e to the positive 4t. Remember, up here it was a negative at, and we have a negative times -4, which gives you positive. So simplifying this, the Laplace transform of this function is equal to -3/16 plus 1/4 times t, because we have t to the exponent 2 minus 1, which is just t. And in the denominator, we have 2 minus 1 factorial, which is just 1 factorial, or 1, plus 3/16 e to the 4t. Okay? So another long one, okay, using partial fractions to solve. But what you can see here is the partial fractions breaks it down into all different sorts of functions that fall within the confines of this Laplace transform table. Okay? Okay, so that was all I had for your Laplace transforms. This is again part 1 of this lesson. Now, I've given you exercises 5 to 24. But what I want you to know here is I don't want you to try questions 13 to 16 yet until the second part of this lesson, which is lesson 4.6, comes out, okay? Because those questions talk about other forms that are specifically related to differential equations, okay? We're going to talk about that in the introduction to lesson 4.6, as well as doing some examples, okay? So if you have questions, please send me a message on Teams or send me an email. Thanks, everybody.